Okay, so here we have three fellows, and looks like the circus is in town because they came over. Look, there they are. The Three Stooges, stand-up comedians. Why are they comedians? Well, because whatever they said just makes you laugh, has to make you laugh. And these people came up with such ridiculous theories that you would think that it's just comedy at its best. You can't take it seriously, okay? Okay, so what are we talking about here? We're saying that these three gentlemen, the guy on the left, his name was, was because even though I brought them in today, they're all dead, okay? And that's good old Heisenberg, Werner von Heisenberg. Guy in the middle, I guess, needs no introduction. That's Heine, okay? Good old Heine. And the guy on the right, that's Niels Bohr. And the two guys on the sides, they're the guys who propped up or began with quantum mechanics or really made it famous. And they're essentially the fathers, the founding fathers of quantum mechanics. You could put Schrodinger in there maybe, but these two guys are really the guys who made it stick because they had what is known as the Copenhagen interpretation, and that's essentially the one that the official version today. Not everybody agrees, but you could say that is the most prominent one out today. The guy in the center, good old Einstein, he didn't believe in quantum mechanics. He didn't like quantum mechanics. He was an enemy of the two guys on the sides. So they did a lot of slapstick among themselves, and Heine never managed to grasp quantum mechanics. And towards the end of his days, good old Heine eventually ended up also, not believing in general relativity. That was the funny part. And I have provided quotes in the past of how Heine spent his last few days, and he didn't believe in quantum or general relativity at the end, which gives me an idea that he was as stupid as all the others. He was somewhat intelligent in that sense. At least he realized something was wrong when he died. Okay, so here we have a fellow. This is how it got me started on this subject. And as this fellow put a comment, okay, and this is his comment, he says, physics is a mathematical representation of reality. Physics is math. And he says, I haven't watched the video. Well, he should have. He probably would have learned something. But, I can't force people to watch videos. He doesn't want to watch. He doesn't want to see a different point of view. Fine, he's already made up his mind that physics is math. Okay, is he right about that? Is that what physics is? Well, everyone from Galileo onwards at least, if not earlier. We have William Gilbert as well, possibly, that already had these ideas. Stevens also, who did the experiment with two weights from a tower in Holland, also had an idea that math was important. He wrote that in his book, 1586, way before good old Galileo. But Galileo did write in his book that, math is the language of God. That's how he explains, actually describes the universe. And so since then, mathematical physics has become simply a description. And if description is science, we're all dead because, you're saying I look at a chair and say, well, it's got 4 legs, a backrest, a seat, and maybe 2 armrests. I can put that in the equation, equal 4L, 4 legs, 1 backrest, etc. I can do that in any equation. Is that science describing a chair? I get a Nobel for that, Nobel Prize. And this guy, to some degree, is right because here you have little Juanito Baez. Talked about him a couple times now, and he created his crackpot index, number 17 in his index, where he says, what a crackpot is. Number 17 says what you see there. 10 points for arguing that while a current, well-established theory predicts phenomena correctly, it doesn't explain why they occur or fails to provide a mechanism, which is exactly what this fellow says. Says physics is math. It's not mechanism. It's not explanation. And good old Juanito here, before he gets deported, he says from his pulpit in UCR, University Southern California Riverside, which is, by the way, state supported. That means you're paying for it with your taxes, for him to beat you up, saying that, look, this is what it is, and I'm going to laugh at you. I'm going to put you in the crackpot index that is in the official site of UCR, right? So people sometimes ask, why, Bill, do you rail against these guys? Well, because they do the same thing, but see, I don't have the power these people have. They put it in their official websites run by taxes, right? They get away with it. But Juanita does agree with this fellow and says, physics is about math. That's what we do. We do math. We don't do explanations. We don't do whys. We don't do mechanisms. Okay, so here, let me give you an example. Okay, here's a theory. It's called the theory of the broken window. Okay, I want you to look at the theory of the window of the broken window. Okay, here it is. Okay, I need to know how that window broke. Fellow throws the bat through it and breaks the window. Now, here's the million-dollar question. Is the mechanism of how the window broke a question of physics or philosophy or who knows what else? Is that a question of physics? Is a physicist supposed to answer those types of questions? You know, if I ask him about gravity, for example, right? Let me take this out. You know, why the pen falls. Juanito says that's not a question of physics. Then who does that question belong? Who do I go to? I want to know the answer to that question. Who do I go to? A philosopher? I thought this was a question of physics. And so let's find out if everybody agrees with him. And here you'll find this fellow, and he does not agree with Mr. Bias. And here you listen to him carefully. He will tell you, okay, whether physics deals with these issues or not. Here it goes.
You're not currently floating around the room. Why are you not floating? Because of gravity, of course. So the ultimate question underneath it all is, what causes gravity? So physics, as you know, this is the type of question, what causes gravity? This is the type of question that keeps physicists up at night. Because physics is, among other things, as you know, the search for mechanisms. Physics is, among other things, as you know, the search for mechanisms. Physics is, among other things, as you know, the search for mechanisms. The reasons or explanations for why certain things happen the way they do, the why and the how. And if a physicist comes to you and says, and asks you, what causes X phenomenon? And you tell her, that's just the way it is, she'll be very dissatisfied with your answer.
Okay. So, does physics deal with mechanisms? Does physics deal with why are physicists interested in understanding why gravity happens, or what causes light, or why magnetism happens? Well, according to this fellow Beecham from some fancy university, he says, yeah, it is part of physics. So we have these differences. It's that Mr. Bias cannot answer that question, so he says it's not part of physics. That's the excuse he uses, he raises, and then he puts it in his crackpot index. So I guess he's saying to Mr. Beecham that Mr. Beecham is a crackpot. Interesting. Okay, another fellow here, he raises an issue, and he says the following. He says, Bill, I've been talking to some chemists interested in thread theory, but they got hard questions. And he goes in there and he says, can you help me understand why the methane molecule forms 109 degrees angles into a tetrahedron shape with zero magnetic moment, etc. Okay, and he goes into other examples, and he says specifically here, what I've imagined is that the tetrahedron is the result of the 4p orbitals, the p orbitals, right? which are the figure 8 orbitals. I'll show that in a second. Spinning away to produce zero net attraction, repulsion with their magnetic threads, etc., etc. Okay, so what can I say about this fellow? I say we got a problem because he says he's been talking to the chemists and they're interested in TT, but they got hard questions. That's when they got me started here, got me going. What's the issue? The issue is that if they're interested in thread theory, if they're interested in the rope hypothesis, they can answer all these questions all by themselves. In fact, all they have to do is compare quantum mechanics against the rope model. And that's where we will see the difference, whether quantum even stands a chance, whether it has any validity whatsoever. Okay, and so the question he's asking about p orbitals. Let's go over some of that a little bit here, so that we understand what the issues are and why these chemists, I doubt very much, are interested in thread theory or the rope hypothesis, because the first things they have to answer is the physics part, whether quantum mechanics stands a chance at all, and if the rope model can replace it completely, because the rope model is a physical model. Okay, that's the difference. Here you can see it. This is what they show. They show these are the so-called energy levels. They also call them orbitals. And the first one there, the one on the upper left, is the hydrogen atom. That's what it looks like, just a ball. Okay. I don't see the electron, but you have to imagine that that's the region in which you can find an electron, that whole ball. Okay. But they got rid of the electron and they just put the ball there and say, hey, yeah, this is what the hydrogen atom looks like, that ball there. And the p orbitals, you see the green ones there, those are the p orbitals. They look like, dumbbells more or less, or, one of those balloons that clowns turn around and, make it symmetric, right? And then you have the d orbitals and so on. Okay, so what are these orbitals? I mean, is that a valid question? Am I allowed to ask that? What are the orbitals? I mean, I don't see them in the standard model. And here you have these orbitals again, and what they're going to do, they're going to merge the hydrogen with the oxygen, which are those p orbitals. They're going to merge the ends of those. And as well as asking, why is there an angle and so on? Well, let's not get to angles yet. We have a bigger or more fundamental problem for all these chemists that are interested in the rope model or the thread theory, right? And the question is, what are those orbitals? They're merging orbitals. Where's the electron? I don't see it. They got rid of the electron. All we see now is orbitals. And they're going to merge these energy levels, and they're going to build molecules with these energy levels. Okay? That's the issue. Okay? So what are we talking about? What are these spirits that they call, energy levels or orbitals or whatever other nonsense they call them? And it gets even worse. Here's the atom. These are real pictures that they took with a scanning electron microscope or with an atomic force microscope. I don't remember which. And there you see them. Those on the side, right? And those are hydrogen bonds. Okay. How did they depict them? They're at the bottom in the center. You see the red and the white with the little white ears, red ball with white ears. And they show the bonds as little arrows, little dotted arrows. So what are those dotted arrows? And you see it also on the upper right. You see that they took a picture of those bonds. Okay, those bond. What does bond mean? Well, bond means that you're going to bind something physically, hopefully, right? You're not binding concepts. Okay. So what you need to check here is that all those little lines, not only are they theorizing that they exist or hypothesizing them, but they're also taking pictures of them. So those bonds, right, are real. Okay, they're real. There's something there. There's a physical object in that region. That's the hydrogen bond. Is that all they have? No, they also have the covalent bonds. Here you see the covalent bond. They took pictures of those. Okay, these are pictures, right? And these are the first picture for the first time, et cetera, et cetera. And you can see the covalent bonds. Something is stretching out there between the atoms that they can take a picture of. Okay, so we're looking at a physical object because if you can take a picture, we're not taking pictures of concepts. We're taking pictures of objects. There is a bond there, and that bond is real. It's a physical object. It's not an abstract concept. Okay, so now you have to identify what is that bond. What is it? Is it a string? Is it a chain? It's an elongated object, obviously. You can't deny that. So what is it? A string? A chain? What is it? And, well, let's find out. Let's go to the standard model and look it up. When in doubt, take it there. And no, we don't see it in the standard model. Where are those bonds? I don't see any of them. Do you? All I see is just names of particles. I don't see the pictures of particles because they all look the same. They just have different colors. But they're all round. They have a letter. You know, like Harvard, you know, the H. Higgs. Okay, so, we don't see the bonds in there. We don't know what they're talking about. We don't see the orbitals? I mean, they draw them as the spheres, as membranes, balloons, but I don't see them there. What is that balloon, that membrane called the energy level or the orbital? What is that? I don't see it there. So it's not in the standard model. It's a big omission because I'd like to know what they are, you know? Okay. So here's our hydrogen atom, a little different than theirs. It is a ball. It's a ball, and you can see there that it's a membrane that encapsulates the atom, okay? And that's our model. And so when we look at, you know, these hybrid atoms or molecules, they look like this, okay? You see the atom right there on the top, so you can see the inside of it. Then you see the atom like it would look like if you had God's eyes. Then you see the p orbital there, okay? And again, you can see the inside of the p orbital, what it would look like more or less. And on the right, you see the water molecule, two H's, which are merged. You know, the balloon is merged with the figure 8 p orbital, right? Which is the oxygen molecule, oxygen element, the element known as oxygen. And you can see all the hydrogen bubbles, you could call them, are all connected by ropes. Okay, so this is, if we had God's eyes, it would look something like this. That's what the water molecule would look like. And of course, the hydrogen bond would be just another rope connecting one of those hydrogen atoms, right, to a p orbital in the other atom. That's essentially it. Very simple, and we're talking about physical objects, not about little beads rolling around creating a region known as orbital or energy level. Okay, so again, we don't have all these energy levels interacting with each other because so far you haven't defined it as an object. You cannot talk about physical interaction if you're going to talk about concepts, dynamic concepts such as orbitals and energy levels. Okay. So here we have it. Let's see. We have a summary here. We have James Bonds here, okay? And we have 007 with his handcuff there and something that connects him. We'll call that the 7, so that's a 007 there, okay? But what do these people say? Well, it's 007 is actually, you know, this water molecule, right? That's connected to another water molecule by this thingy they call the hydrogen bond. Okay, what is this hydrogen bond? Well, again, they just put it in there by hand. They sometimes even put an arrow or double arrows. What is that? We have to identify. We need to find out what that is. And here we have the same thing with the two atoms. I mean, we removed the hydrogen bond, but there you have two hydrogen atoms. What connects them? You know, I mean, what are we going to put in there? What is that 7 going to be there in that case? Okay, so you see the problem that these people have. They don't identify the physical objects, but they've taken pictures of these bonds. Okay, and here you have our model. Okay, that's the 007. The 7 is the rope. Okay, so we have 2 O's and a 7. No problem whatsoever. So we do have a little difference with the establishment in the sense that we have identified what that bond is, what those hydrogen and covalent bonds are. They are the ropes. But in the case of the in the case of the covalent bonds, you have many ropes, And that's why they were able to take a picture of that. They are able to take not of one hydrogen atom, but they can more or less see that something is starting to stick out of there. And again, because you can imagine that there's this little bird's beak coming out of the atom, and that's essentially what they took a picture of. They can't take a picture of the hydrogen bond itself. I doubt very much they'll ever get to that level. But yeah, there is this you could say a bird's beak coming out of the atom that's connected to the other atom. But again, what we're talking about is a physical object. We're saying that these bonds, hopefully bond refers to something that is physical, is a physical object, and that's why we were able to take a picture of it. We can't take pictures of concepts such as energy levels or orbitals. Okay, and so here let's go a little deeper into this. Here we're going to have what an orbital is. Okay, so we get the picture perfectly of what quantum mechanics is doing, what all these great men of science are doing. Here you have a boy swing a little stone around, or a little ball or whatever, around a string or an elastic or whatever. Okay, no problem. Okay, now what we're going to do, we're going to look at the region. Okay, that's the region, okay, that the ball or the stone or whatever he's got there, describes, or that's the volume in which of space, you could say, in which you can find it. Okay, so let's get rid of the boy and the stake now. Okay, that's what we have. Okay, we have just the region now. We have the energy level. We have the orbital. Okay, we got rid of the electron B. We got rid of the boy swinging the little stone around. Now we're going to deal only with the region. It's a region now. Okay, and here we have one region just touching another region. We're going to have two atoms there, essentially, the electrons of two different atoms. They have all these regions in which you can find them, okay, according to Heisenberg's rule, okay? Schrodinger's rule, okay? Okay, and so what do we have next? Well, we have, here, let me put them in motion now. Here we have them. You have these regions interacting with each other, okay? This is what they're saying, that you have these atoms moving around, but they interact. The regions interact. We forget about the electron because now we're only going to deal with the balloons, with the regions, okay? And yeah, it gives you an idea of what these people are trying to tell you. They're saying that regions interact. And here, let me show you how they do it with the atom itself, okay? Here you have the atom, okay? That's your regular atom. You have these regions known as orbitals or energy levels, and the electron bead can be found within that region, okay? It falls to a lower region, emits some energy, and then it rises and absorbs energy. That's the quantum jump. But that is your atom there. Okay, and so here we have it. Okay, we get rid of the proton and the electron. We're going to remain only with the regions. Okay, we're going to be dealing with the regions because they say that in chemistry, it's the orbitals that interact, not the beads. Okay, and so here we have two atoms now. Okay, it looks like they're interacting somehow. They're meeting each other or blending, or who knows what they propose here. Okay, and here we have them moving around. Okay, if I can get it here. Okay. So these regions are now interacting. They go back and forth as atoms, do. And when they're close, they interact and they separate and do all these fancy dances. Okay? This is what they're saying. And so the question is whether it makes any sense to talk about bonds and regions having all these interactions. The James bonds, these hydrogen and covalent bonds, they're bonding. Physically bonding two atoms together, or sometimes molecules. And you have the regions, and they merge. And region is a concept. You can't say concepts merge. You don't, merge love with hate. It's very difficult to do that, or love with love, for that matter, right? Very hard to merge concepts, and this is what they're doing. They're merging concepts. Okay, so what do we have? Well, we have good old Einie who disagreed with quantum absolutely completely, the conclusions. He was a guy dedicated to this stuff, which is, the space-time thingy, four-dimensional. They always draw it in 2 dimensions, which is quite a bit of cheating there. They say time and they put 4 dimensions of space. None of them are dimensions, by the way. They're all number lines. And they're going to bend this thing. They're going to say the reason the Earth doesn't fly out of the, or the moon in this case, doesn't fly out of the solar system is that it's space-time is warped by the Earth. And this means that the moon is hitting some kind of a brick wall, bent or warped brick wall made of time, made of seconds and minutes and years and who knows what. So this was his proposal. He didn't agree with quantum mechanics, so he's the father of this stuff. Okay. How about the other 2 fellows, Heisenberg and Bohr? Well, here's Bohr. What did he come up with? Well, together with Rutherford, he came up with this ridiculous atom, the planetary atom, which is still used today. The only difference between Bohr's atom and the one they say today, because they say, oh, we don't use Bohr's atom. What are they talking about? Are they saying that they got rid of this completely? No, what they're saying is it's not a circular path. It's not a circular orbit. That's all they're saying. They're saying, look, you can find the electron bead anywhere within that volume of energy levels or orbitals. That's all they're saying. It doesn't, in other words, it doesn't orbit in a circular or consistent path, constant path like a planet would. That's all they're saying. But they're saying you can find the electron bead anywhere within that volume. And to find out where it is, you have to use Schrodinger's equation. That's all they're saying. The atom is the same thing. It's a planetary atom because they have the electron bead next to the proton bowling ball. All they're saying is you can find the electron somewhere in there. That's it. That's the only difference between the Bohr atom. And here's Heisey. What did he come up with? Well, he came up with the uncertainty principle. And that's that equation there at the upper left. And we don't care about that, cleaning our nose holes with it. What he's saying is when the ball moves, it doesn't stand still. And he's right about that. I can't see it standing still. And when the ball stands still, it doesn't move. That's essentially what Heisenberg says. Okay? So he got a Nobel Prize for this. So yeah, thank God for Nobel Prize. Yeah, that's what he said. So what do we have from these fellows? What comes out of all this? Well, you would say, okay, we have a law, some kind of rules that we can sink our teeth into, some kind of physics that you can take to the bank. This is the result. This is the conclusion. The interpretations of quantum mechanics, they have 500 million interpretations. They have the Copenhagen one, which is probably the most popular one, the one that most so-called, mathematical physicists vote for. You have all these variations, the measurement problem, the quantum mechanics, non-locality. You have the hidden variables, Bayesianism and so on. All these are the different versions of quantum mechanics. And why they just have these different opinions. What are these? These are physical interpretations. Of course, none of them are physical because all they're talking about is equations and concepts, so not one of these is a physical interpretation. But, more than that, they're all magical. They're all magical because they're using concepts as objects, and then the mechanism is not explained. Like, you have things such as entanglement. One particle over here affects another particle. This one over here affects this one over here without anything in between them. No bond, no energy level, no balloon, none of that. This one just affects that one. How does it do that? And in science, we call that black magic. That's how they do it. They say, it just is, it just does, it just happens. This particle affects that one, and we don't know how it happens, and we call it entanglement. And we proved it in the lab. We run technology based on that notion, but we don't know how it happens. And that's like saying, that you take a magnet and you pull up iron filings and you say, hey, I can use that for some technology. I can lift cars or whatever with a magnet. How does it do it? Oh, we don't know. We have no idea. We don't care, but we're making money. And that's more or less where we're at today. We have no explanations for how quantum mechanics runs, in great measure. Why? Because these great scientists who set us off on on this course, quantum mechanics, they relied on these irrational notions. They just did concepts, they did math, they did equations. They forgot about the objects. They never defined what an object is. They don't care about it. And then they wonder, why can't we explain it? Well, you cannot explain it because you need objects and you never define what an object is. You need to know, you need to understand, you need to define what an object is. And once you do that, now you can say, okay, I'm going to use this object as a mediator or whatever. And you can see the mediator has to be an elongated one. It's got to, if you're going to do bonding, between two molecules, if you're going to have two balloons, like energy levels and orbitals interact, you had better make them into balloons or some kind of physical object. What are those energy levels? I mean, if you're going to have them interact, what is it? And again, they've never defined these things, and that's why we have no explanations. That's why people like Bias says, we don't do explanations. Why? Because he cannot explain. And he just wants to describe using math, which is what they do, but that has very little to do with physics.